Well, welcome everybody. I guess we should get started here. You should be in data structures, either CSCI5555Fall2017L1P1 or 5555. So how many graduate students are there? That's right, we just have one. And everybody else is in the second, the 2232. So I take it you guys are sophomores. Was there a freshman? Did I see a freshman? No? Okay, so you guys are all sophomores. My name is Bill Phillips. I'm your instructor. This is my fourth year at Fairleigh Dickinson. I've mostly been teaching graduate level classes, but I guess this year our graduate enrollment has fallen off quite a bit. So now I'm teaching some undergraduate classes, that's fine. I taught C++ at NJIT, where I graduated from in 2015. After that, while I was working on my PhD, I took a year's leave of absence from the program, and I worked up at Harris Communications in Rochester, New York, on their software-defined radios, doing C++ programming. And I also taught intro to high technology at St. John Fisher up there to a number of undergraduates, mostly people not in the computer science area. Then in 2015, I came to Fairleigh Dickinson. As I said, we had a huge influx of graduate students. So I've taught software engineering, operating systems, systems programming. I've taught software configuration management. That's a course that I put together as an elective to kind of help with the overload of students. This summer I taught pre-calculus. I've taught that twice, so I do have some. I do have some experience with teaching undergraduates. Okay, so my office is in this building. My office hours, as it says, Monday, Tuesday, 10 to 12, Wednesday, 2 to 4, but I recently moved, so I live really close to the school, so I like to spend a lot of time here. So even if it's not office hours or you haven't made an appointment, you should just come up and see if I'm in. Well, it's funny, it's funny, the spell checker wants to spell appointment with an E like that. So anyway, the spell checker thinks that's right. The required text for this class is the Dale Nell book. Let's see. I have it down here. This one. This recommended text, starting out with C++, early objects. This is the book that I used when I taught C++ at NJIT. So I think it's a pretty good book. It says 9th edition here, but actually when I taught the course, I used the 7th edition. So, if you're interested, you could get this book. I think it's, this book, it's okay, but this book kind of goes into the C++ language a little bit deeper than this book does. And also, as we go on, I will probably be using some slides from this book. And, since I've got some homework examples already in place, from the time I taught this at NJIT, I might just go ahead and reuse some of those. So anyway, yeah, if you're interested, that's a good book. I think like I said, they're up to the 9th edition now, but I can't imagine that book has changed that much. Right. So I don't really know why they don't call this course Algorithms and Data Structures, but anyway, I guess they've decided not to. The course description, we'll be looking at some abstract data types used in computer science, in particular arrays, character strings, stacks, queues, linked lists, trees, graphs, and file structures. We'll be looking at searching, sorting, storage management, structure, and selection. So I teach algorithms, CSCI5555Fall2017L1P1, and so in a way this course will kind of be algorithms light, we'll just kind of give you an introduction to these things called abstract data types, what they are, and how they apply to computer science. So just quickly, like an abstract data type, probably one of the simplest abstract data type. Let me adjust this a little bit so you can see this. I just need something darker. So an example of an abstract data type would be a stack. So it's like the data structure to implement the stack is hidden within the abstract data type. And then we provide functions like push and pop and top of stack. So that's like an abstract data type. How we implement the stack, we can do it a number of different ways. We can use like an array. We can do it as a linked list. But the data structure that we choose to implement the stack can affect the performance of the operations of the functions like push and pop. So that's what we mean by abstract data type. Let's see, maybe turn on the light up here. Okay, I guess that's better. Okay, so we have the operations, and like is empty returns true if there's nothing on the stack, etc. So this is an abstract data type. Others are like queues, priority queues, dictionary lookup functions. So that's what we mean by abstract data type. And we'll be working with those later in the course. Prerequisites, I guess CSCI1202 or Info 2102. I haven't taught a lot of undergraduate classes, so I'm assuming that you guys have met the prerequisites. At the completion of the course, you'll have a practical understanding of the concepts of data abstraction. And again, we'll talk about what data abstraction is and what levels of abstraction are and how those apply to software engineering and programming. An understanding of the proper use of C++ constructs to implement abstract data types. So in particular, if we're working in C++ and we want to implement a stack, we would typically write a C++ class where we would define internal to that class the data structure that we were going to use to implement the stack, and then with that class we would define methods that we would use to access the data structure. A key thing about object-oriented programming and using an object-oriented language like C++ is whatever data structure that we choose, we want to make sure that the only way that you can access this data structure is through the operations that we provide. You don't want to have outside entities come in and directly access this data structure. The reason we want to do that is because when we're building a software project, we can, as we construct the software project, we can implement our stack and use a simplistic implementation for the stack. And then later, we want to be able to come back and change this implementation. And if we define the abstract data type like this, we can change the internals, not change the methods, and it's like we can replace this. So if we were doing a sort, it's like we could have like a sort abstract data type, and here we have like the routine sort, and then we might here we might have input record. So we could call input record a bunch of times, store it in an internal data structure, and then call sort, and then the sort function could sort this. Initially, we might use a slow sort, like bubble sort, but then, if we found if we found like the number of records that we were sorting got to be too large, and bubble sort started taking too long, then we could come in and replace the sort algorithm with a faster one, like merge sort or heap sort, to speed it up. So that's the idea behind abstract data types. It's information hiding. And so it's like we want to keep these internal, the internal implementations hidden from the outside user. Okay, and we'll have some exercises where we will implement some abstract data types. So you'll have an ability to develop C++ programs of moderate complexity. There is a big debate whether it's more advantageous to have you create programs from scratch, or is it better to have a framework that you work within to add classes to and to enhance those classes? I kind of think that's better because I have a lot of years experience in software engineering, and very rarely do you get the opportunity to go in and develop a program from scratch. You're always working within a framework. For instance, the last project I was on, there was a software communications architecture that we had to work within. So, you know, it seems like you're always constrained within some framework, but we'll do a little of both, I guess. You know, just to give you the feel for working on programs from scratch and also adding classes and functionality to an existing collection of classes. We'll be talking about dynamic arrays, stacks, queues, linked lists, binary trees. We do this in algorithms too, except I think, you know, in algorithms we dive a little bit deeper into how long it takes to traverse a linked list. We do a little more analysis of using a binary tree to store data. And, you know, dynamic arrays, you know, some of their properties, and, you know, just go a little bit deeper than we will in here. And then we'll go over searching and sorting methods and how they relate to the type of data structures used. So that seems fair. I have two different grading scales. We'll have the graduate student do a graduate project, which will be 10%. The rest of you will not have a project to do. It will just be homework, which will consist of both programming exercises and some questions taken out of the book. We'll have a midterm and a final. The midterm and the final will be closed book, and I always do the blue books. I know some instructors do like online multiple choice, but I just kind of, I've always been subjected to the blue books, so I think, yeah, that's just what I'm used to. So we'll do that. This is the grading schema, or this is a grading schema. Use this as a guide. You can count on, like, if you get 90% on all of the work, then you'll get an A in the class. If you get a little less than 90, you might also get an A in the class too. So this is like the strictest grading schema that I'll use. I'm kind of an easy grader, so, you know, just I usually like take this and kind of map that into A to, like, I guess for undergraduates, C, you know. So, but just keep this in mind, and just, you know, consider this to be the grading schema that we're going to be using. So today we'll be talking about software engineering principles. Next week we'll be talking about data design and implementation. I think it's actually, instead of class notes, it should just be chapter 1 and chapter 2. I guess we didn't change that. I think the previous instructor went off class notes for the first 2 weeks. So here I'm just going to follow the book. So you should be able to just read the book and cover what we go over today and next week. So maybe we can correct that. And then we'll look at these abstract data types: unsorted list, sorted list. And so, you know, again, you think about like a sorted list. You're putting data in to the abstract data type, and then when you pull the data out, you expect it to come out in a sorted order. So when you put the data in, you can keep the list sorted, or when you pull the data out, you can search through the list and get the next entry and return that. So we'll look at the consequences of implementing a sorted list a couple of different ways. Week 5, we'll look at stacks and queues. Week 6, lists. linked lists, either singly linked or doubly linked. And then Chapter 7 is programming with recursion. And then week 8 we'll have the midterm exam, and the rest of it you can say. We're just basically following the book, and the chapters are listed on the right there. I do want to spend some time with the standard template library. It's an important aspect of C++. That's known as generic programming. It's a little bit different than in making classes and creating objects from classes. Generic programming was a feature of one of the early versions of Ada, where you didn't have the ability to create objects from classes. But still, that's a good way of being able to implement the abstract data type. So in here, we might write the code to implement a doubly linked list, but in practice, what you would do is you would use the list that's provided by the standard template library, and so just implementing it yourself will give you a feel for what it is, but if in practice, if there's ever like an abstract data type in the standard template library, a lot of times it makes more sense to just use that. And then final exam on the 15th week. Homework and supporting documents. It says course information, but that's not correct either. The only thing that's in course information is the syllabus. I like to work out of course documents, and in here you'll have the slides for today. This is where I will put the assignments, whether they're programming assignments or whether they're answering questions out of the book. When I create an assignment, there'll be a due date associated with it. I try to give plenty of time for you to do the assignments. There'll be instructions for the assignments, how I want them turned in, and you'll submit them into course documents. So you'll see there'll be an assignment, and then there'll be a place where you can turn the assignment in. I always fix it so that you can make multiple submissions into the assignment. So the last one submitted will be the one that's graded. There's a due date. The assignment remains up for 24 hours past the due date, and then at that point the assignment goes away. So I give you the 24 hours because usually I just set the due date and it's due at 12 o'clock midnight, but a lot of times they do maintenance on Web Campus, and for whatever reason the website is down. So that's why I give you 24 hours past the due date to turn it in. After that, the assignment is late. Well, I think I discussed this in the syllabus, so I should just go back to this. Okay. Okay, well, I guess we don't have a section. I just kind of borrowed the syllabus from the last guy that taught this. I guess he didn't have a late, what happens with late assignments. If your assignment is late, please don't just email the assignment to me or the TA. Get in touch with the TA, and her email address is BURA_SRI at student.fdu.edu, and we will still can't see that very well. And most times so it's BURA_SRI at student.fdu.edu. We're pretty good about taking late assignments, but again, it's just kind of up to the schedule of the TA, and if we might have a grader for the class. So please just, again, it's like I tell them, like, if the first thing you do is email the late assignment, then don't take it, but a lot of times they do anyway. So if you have a medical excuse or an emergency, let me know, and we can accommodate that. So just try to get your assignments in on time. If not, contact the TA. The only rule is, it's like the only way you can be absolutely sure that an assignment is going to be counted is to get it on time into Web Campus. Sometimes, like at the end of the semester, students will submit things while I'm in the process of calculating the grades, and that assignment doesn't get counted into the grade, and I'm sorry, it's like you just shouldn't have been late. But for the most part, just contact her first. The other reason why I don't like to take assignments by email is it's a good way for them to get lost. A lot of times, you send in an assignment and it goes to junk or clutter, and I don't see it. So it's just kind of my policy to not take assignments by email. So she'll let you know how to turn in the assignment. This is the attendance and withdrawal policy. I don't know about this. The rules are out there on the website. It's kind of up to you to know what they are. So I guess if you withdraw within a 9-week period of a semester, you'll receive a grade of W. Anyway, so this is between you and the school. I really don't have anything. Really don't have anything to do with that. If you can't attend a specific class, you really don't need to notify me. I record the lectures, so I'm recording this now, and I'll post the lecture generally within a day or two to Web Campus. So if for some reason you can't attend a class, it's better that you do, but again, I record the lectures, so they're available for you to go over what we covered in class. I don't do that so that you have an excuse to miss class, but it's just in case you don't understand something the first time we go over it. You have the opportunity to see it again. Let's see. Oh, if for some reason you're going to miss an exam, let me know before the exam. Then I can accommodate it. So just let me know, and you should really have a reason for it. In my graduate classes, sometimes the students get positions and they'll be outside of the area. So then I kind of have to make special arrangements for them to take the exam. But I think in here, this is kind of a beginning class for everybody, so that really shouldn't be a problem. The other thing I tell my graduate students, and I guess this goes for you too, it's like if you're in some kind of an academic problem where you need a specific grade out of this class, come and talk to me, and we can keep an eye on your work, and we can potentially give you like a second chance to do an assignment. Again, I don't really know how much that's going to apply in here, but a lot of times the graduate students, they have to keep a certain grade point average in order to get a scholarship or graduate. So it's just, but it's like I tell them, talk to me before the class as opposed to after the class, and we can take steps to accommodate that. These are the academic regulations. I always go over these before the class starts here. All right. So you guys should all know what academic dishonesty is. Giving or receiving unauthorized assistance in any academic exercise or examination. So both people are guilty of cheating. If somebody's looking on a paper and the other person lets them look on a test paper, that's cheating. We don't really run into things like plagiarism, where we don't cite references for a paper the way that we should. You usually don't see that in computer science. So it's mostly cheating and turning in work that's not your own. All right. And so, for the most part, again, it's like either copying somebody's assignment. Sometimes I get assignments and the person doesn't even bother changing the name on the assignment. So it's very easy to tell when you've got a duplicate assignment. We don't have that many students in here, but even when you're grading a bunch of papers, it's really easy to spot the same answer given. So just, I don't mind if you collaborate, but just, don't just copy from somebody and turn in a duplicate assignment. It's like all the work in here will be of an individual nature, so I don't think we're going to have any group projects in here. So that's here presenting the work of another student as one's own. First time that happens, the sanctions are you get no credit or failure for the academic exercise. Reduced grade for the course, failure in the course, or recommendation for the recommendation for academic probation to the dean of the college in which the student is registered. So it's like I'm supposed to pick one or a combination of those, and then in addition, I'm supposed to file a notice of the penalty in your student's file maintained in the campus Office of Enrollment Services. And the reason they do that is because the next time, then you're talking about dismissal from the university. Suspension for a year, dismissal from the university, or dismissal from university identified on the transcript. So just, I don't know. It's just not worth it to cheat. And even if you have an instructor that's kind of lax about this, it's like eventually you're going to run into an instructor that's not, and you just you really don't want to go down this path. So again, collaboration is okay, but don't just copy somebody's work and turn that in. Do your own work. Okay, any questions on any of that? That's just pretty standard stuff that you should be getting with every class. Today is just kind of meant to be introductory, so I have a set of slides that will kind of introduce me, give you some of my background, some general information about software engineering, which I I have a lot of experience in industry as a software engineer. Again, I've just recently become a college professor. It was kind of like my lifelong goal to want to do that. So as I mentioned, I just recently, in 2015, completed my PhD at New Jersey Institute of Technology. I have over 30 years in industry as a software engineer. Most of that I was working as a contract engineer, and that means if you look at my resume, I think the longest job I ever held was like 3 years. Most jobs that I've worked at have been like a year or a year and a half. The reason I did that is because typically those jobs, at least in the past, have paid a lot more. So, it's a trade-off. You get a lot, you get a lot more money, but you have to be a lot more mobile, and you have to move around the country a lot. But it can be rewarding, as opposed to being with a company for 20, 25 years and then retiring. There's no way I could do that. I know I saw some guys at Boeing, it's like they graduated in like 1972, 73. They got their first job there, and they just remained there for a lot of years, working on an old IBM mainframe. I always kind of was after the latest new state-of-the-art project for the money, and also to keep my skills current. Languages I've worked in, assembly language. It's like we use assembly language in the thrust management system for the 757, 767 aircraft, which I worked on. I've worked in Pascal. When I graduated with my undergraduate degree in 1979, Fortran was the language that was really out there and prevalent. Jovial came along. Joule's own version of interactive algorithmic language was a precursor to Ada. Atlas was an automated test language for some kind of systems. I forget the acronym. C, C++. My last job was working in C and C++, Java, Python. And when you work on a large software project, sometimes you can identify design patterns that you can create an application-specific language compiler where instead of having machine language as the target language, the target language could be C or C++. An example of this is if you're familiar with Corba, the IDL, the Interface Description Language, is an example of an application-specific language. I think they call them domain-specific languages now, but you have like a language that you feed into this compiler, and then the compiler will output C++ classes that you'll build with your software. Another example is RPCgen in the Unix operating system. If you're doing RPCs, you have a language that you feed into the RPC compiler, and it will generate C code for you that you write code against, and then you can do remote procedure calls to other machines across the network. I started college in 1972. That's when I wrote my first program in Fortran at the University of Washington. And you probably heard the stories where you have the key punch machine. So if I were to write a simple program, it's like you have to sit down at a key. We start with a coding pad, and you write out each Fortran statement. Then you go to a key punch machine, and for each Fortran statement, you punch out. This key punch machine makes a card, So you'll have a deck of cards, and then you take this deck of cards and you submit it to the bin at the computer room, where the operator takes your cards, feeds it into the card reader, and then you get your cards and a printout back. And then you'll have, the first thing is you'll have a compiler error. So you'll have to do this 5 or 6 times to get the compiler errors out. And then you'll have like a runtime error. So just writing a simple program, you got to give yourself at least 3 or 4 days. And you learn to go to the computer center late at night where there's not a lot of people around, so you can get the fast turnaround. And so that all through my undergraduate career, that's how I programmed a computer. They really didn't have computer science as a discipline at all of the colleges at the time. So my undergraduate major was in math, numerical analysis. So it was a good major at the time because we were programming mathematical problems like matrix problems and differential equations and curve fitting. So it was good training. I'm a lifelong learner. I've been in one class or another all of my life with the idea of becoming a college professor. In 2009, I started my PhD, and I graduated in 2015, and I worked with a professor at NJIT in the field of global optimization algorithms. Global optimization is concerned with finding the minimum or the maximum value of a function, and these problems occur everywhere. So for instance, like in the financial industry, you're interested in maximizing your profit given a set of stocks. You want to be able to come up with an algorithm that will help you pick stocks. These algorithms abound. Okay. All right. So, like I said, I like the Gaddis book. In addition, that's a recommended book. It has a lot of good reviews from professors and teachers. And it also reminded me of one of the best books that I used to learn C++. The last part here doesn't really apply. This is for intro to computer science, so don't worry about that. All right. So the homework will come from the book and from the Gaddis book and maybe elsewhere. Maybe we'll take a look at some design patterns. It just depends if we have some time at the end. When you work on a large software project and you do the design, design patterns will start to emerge. And also there's a collection of well-known design patterns that you can use to help you with the design of a program. It's a very important part of software engineering. So if you decide you want to go into software engineering, plan on learning some of the major design patterns, know how to document them, and again, you will find them occurring in designs that you create if you ever work as a software designer. I have some coding standards that I would like for us to follow. These are outlined in the slides. I would recommend reading this book just to see like what coding standards are. If you ever work as a software engineer, I can guarantee you about the first thing that will happen is your supervisor will point you to or hand you a copy of the coding standards that you have to follow. I have just a few that I would like for us to follow. If you violate the coding standards, it's like we're not going to downgrade you, but we'll most likely point those out. just to have in your mind, like when you're writing code, to adhere to coding standards. So I have this book. If you want to take a look at it in my office, that's fine. I think I might also have this on reserve in the library. If not, maybe we'll take a look at getting a copy of this. So remind me, and we'll see if the library can order it and put this on reserve. So today's lecture is on software engineering. That's chapter 1. But it's like I have some things I'd like to say about it that I don't think they really cover in the book. In the early days, software was viewed as an afterthought, and it was something that was performed after the real engineering was done. So they would, it's like when they would schedule an embedded system that had software in it. It's like the schedule was geared towards getting the hardware completed. And then after the hardware was completed, then, okay, great, well, we're done with the project. All we have left to do is just put the software in it. This approach led to the software crisis, this term was coined in 1968 by Edgar Dijkstra. He's a famous computer scientist that has given us a number of algorithms, like Dijkstra's shortest path algorithm that you find in routers today. A router gets a packet. It wants to know the shortest path to the target router. So Dijkstra's algorithm is used for that. He gave us semaphores, which you will study if you take operating systems or systems programming. He invented the dining philosopher's problem, which you will also encounter if you take operating systems. The discipline of software engineering was created around 1979. Wikipedia says that the first Master of Software Engineering degree program was established at Seattle University in 1979, but I actually think it was established at Wang Institute of Graduate Studies in Massachusetts, but since then that institute was taken over by another college, so that's probably why Wikipedia didn't give credit to that. This program was heavily supported by Boeing in Seattle, and the reason is because of the software crisis. They had a number of embedded projects, and they really needed to bring in some discipline in doing software engineering, so they heavily supported the MSE program at Seattle University. So I graduated with one of those degrees in 1985. And the thing is, it's like it was a degree program that you had to be working in the field in order to go through the program. So, I was at the time. So what is software engineering? It's planning and defining a software product. In the book, we're going to look at some software lifecycle models, waterfall spiral, iterative enhancement. And my research area up to this point has been doing software engineering in the academic environment. So far, we've done 2 software projects here at school. We did the requirements analysis for a predictive wastewater management system. And right now we have a software engineering project underway where we are implementing a Java FX program and associated math model for a company called VMC in Bloomingdale, New Jersey. So just a quick background on that. They make shock isolation units for military equipment. And what they have now is they have a math model that's implemented as an Excel spreadsheet. So when somebody wants to order one of their isolation units, they call up an engineer, and the engineer has to sit there and run this math model with the person on the phone. Well, we're trying to automate that more and come up with a Java FX application that can be either run on a website as a standalone program or running on iOS or Android. So that's the big thing about Java FX. It's supposed to be portable to a number of different platforms. So we have that underway now. I don't know if that's going to continue or not. I'm thinking like maybe like one of the other professors may approach them and see if they'd be willing to pay us some money, because up to now the work we've done has just been done as advanced special projects. So at this point, it's kind of like they need to pay if they want more work done on it. Well, anyway, so where that was going is I also have created a software lifecycle model that we follow for doing work in the academic environment. We use an agile approach, and I'll show you a diagram that documents that when we get to the lifecycle models. Software engineering is concerned with documenting, with splitting the project into phases and creating deliverables after each of the phases. We're concerned with validating project phases. These DoD standards, I don't know if they're around anymore, but in the 2000s, these were the ones that were followed. If you're doing work for the government, the government has documents and things that you have to follow in order to get paid for the project. So typically you're paid at the end of each phase. So a lot of times you're stuck with the waterfall model, although it has its the waterfall model does have its downside. A lot of times you're forced to do that by the customer. We have languages and automated tools for specifying requirements, tracing those requirements through the software configuration, and we have languages and tools that we use for design. So I'll probably give you a copy of Rational Rows 98. It's kind of outdated, but it has the basic features in it that should suffice for the work that we do in here. We're not going to really go deeply into all of the features of the unified modeling language, but we will probably use it in order to specify and document the classes, the C++ classes that we create in here. So there's a number of those. Rows is my favorite, just for whatever reasons. It just seems like it's the easiest to use and gives you just the right amount of information. Others are like Magic Draw and Rhapsody. You'll see that like in job ads. The thing I don't like about Rhapsody is like when you do reverse engineering on a software project, it just gives you too much information. Magic Draw doesn't give you enough, but Rational Rows seems to give you just enough where you can reverse engineer a project and then get an idea of like what the designer was doing. All right, so software engineering is concerned with product acquisition and managing the software project. We have tools for that. Reusing software, again, that's like design patterns is an important aspect of that. Software configuration management is a very important aspect of software engineering, which is overlooked by a number of academic programs. So as I mentioned, it's like early on, I created a class in software configuration management, and I think I taught it like 3 or 4 times here at the school. So as our graduate population has been cut back, they've kind of cut back on the electives. So I don't I don't know that I'll be able to teach that anymore, but it is an important area. If you look through job advertisements, you'll see things like DevOps, and that what DevOps is getting the development organization to work with the operations organization. So the development organization develops the software. The operations group is in charge of the operational baseline, which is out there that the customer's working with. So, again, you'll see DevOps all over the place when you look through job ads. Software metrics, if we're going to take on a software project, it would be kind of nice to know how long that the software project is going to take. So there are tools that will help you try to get a handle on how long the software project will take. Barry Boehm created the constructive cost model around 79, 80, where it's a model where you input attributes about the software, and it spits out how many lines of code that the software should take, and then from that you can arrive at an estimate. So Wikamo was a software program that that automated the Kokomo model, and the WI stands for Wang Institute. So that's that Wang Institute of Graduate Studies that I mentioned before. They actually produced the Wikamo model. Function points was a model created by IBM, and this T. Capers-Jones created this SPQR tool. All of these are concerned with trying to get a handle on how long a software project is going to take to accomplish. Other aspects of software engineering, Carnegie Mellon has a capability maturity model. I think there's a new one now, capability maturity model integrated, but this old one would, you would have like an evaluation team come in, and they would give your project a grade from 1 to 5 based on the software processes that you had in place. So it's just a measure of how mature your software project is. So it's kind of funny. You're working on a project, and management would come down with an edict. I want this project to be optimized within 2 months, and so it just kind of gave me an idea that he had no idea of what you had to go through in order to actually reach the optimized level. I always looked for projects that had a grade of 3, and I think that was really best for those of us working in the field, because there were processes in place that kind of held the project together. But when you get into the higher levels, it's like, in addition to getting the product out, you're spending a lot of time collecting and archiving data so that they can come up with a higher maturity model rating. I kind of like the ISO 9000 standards. Basically, what ISO 9000 is it's a set of international standards. ISO is International Standards Organization. And the thing about ISO 9000 is you're supposed to say what you're going to do, and then you're supposed to follow what you say. So the framework we use here for developing software, you could say that is ISO 9000 compliant, because we have documents in place that define how we develop software. Some architectures you'll encounter, like when I was working up at Harris, everything was done to the software communication architecture, where it's like they define what a device is, what a resource is. They give you classes that you have to create, C++ classes that you have to create to model the devices and the resources. It's stated that you have to use minimum corba and that the operating system has to be POSIX compliant. So just basically, you're just not allowed to write the software from scratch. It's like you have to adhere to a particular architecture. So software engineering is you're writing maintainable, understandable, testable, reusable code that meets requirements. And you also have to document the requirements and document a design wherever they come from. These requirements may come from you, like if you're designing a new app that's going to run under Android. But in here, the requirements will come from me. So the requirements will come in the form of homework assignments. And so I'll do my best to communicate them clearly. I'll tell you what the assignment is. And in particular, it's like I will give you instructions as to what is to be turned in. And I think in here, a lot of times that will be a virtual studio project placed in a zip file so that the grader can just download that, unzip it, and then run it to make sure that, that the program was implemented correctly. But again, it's like with the look in course documents. I will do my best to send out an announcement when an assignment is posted there, but sometimes I just don't get around to doing that. So frequently check the course documents area in Web Campus. This is also where the lectures will be posted. Again, it's like it's like what you'll see when you look at the recorded lecture is you'll hear me speak, and then you'll see whatever's on the screen here. Here are some phases, software engineering phases, and the book slides discuss these too. But basically, we have like a phase where we are eliciting or gathering requirements. That is where we determine and document what the software is supposed to do. Then there's a design activity, high level and low level, or high level and detailed, that tells us how we are going to do it. And typically out of the design activity comes a detailed design. And for us, it's like it'll be a UML diagram showing a number of classes and how they interact with each other. And then from that detailed design, we should be able to translate the class diagrams into C++ classes. Once the design is done, then there's a period of coding and unit test where we turn the design into code. And it's important to realize that these steps don't have to necessarily occur one after the other. With waterfall, they do, and again, we'll see that in the book. With the waterfall model, you do requirements, then at the end of requirements, you do design, then at the end of design, you do coding and unit test. But with the more modern approaches like Agile, it's like you'll determine a subset of the requirements, and then you'll carry that all the way through implementation. Get another subset of requirements, carry those all the way through implementation. The idea being when you do that, it's like every time you do one of these Agile runs, you learn from it. And so the problem with waterfall is you can, it's like if you do all the requirements first, do the design next, and then do the coding, and then you deliver this big product, and then the customer looks at it and, well, half of what you got is good, but the other half I don't like. Well, now you got the problem. You got to go in and try to remove the part that they don't like and keep what they like. But with the Agile approach, you do a little at a time. And if you do something that they don't like, then you can just throw that out, learn from that, and then on the next Agile run, correct that. And so it's like you're doing a little at a time so that, you're learning as you go and you're exposing the customer to the product as it evolves over time a little piece at a time. But again, like if you're on a military project and you get paid after doing the requirements phase, and then you get paid after the design review, then you're kind of stuck with this. So, and then there's a number of levels of there's a number of tests that correspond to the what we call artifacts, man-made things that are deliverable after each of the phases. And so that varies depending on whether you're just doing a software project or if you're doing an embedded project where you're delivering hardware with software embedded in it. Then, of course, there's going to be a lot more testing phases. Inherent in software engineering is teamwork. So I always say that on a large software engineering project, trying to get the people to work together in an organized manner is much more difficult than any technical problem you're going to encounter. Technical problems, those can be solved by, if you don't have the expertise in-house, it's like you can always bring in a consultant or somebody from the tool set that you're working with. But if you've got a mismanaged or a software project where the people just aren't working together well, then that's a very difficult problem to solve. Also, you'll inherent in a modern software engineering project, you'll have reviews of artifacts. So the book talks about inspections and walkthroughs. You're likely to encounter that. And controlling the deliverables, very important aspect of software engineering, and that falls under, again, the category of software configuration management. You have to control what's being delivered, and you have to be able to recreate it. And it gets particularly difficult if you're writing software that's going to run on a number of different platforms. So that can quickly get to be a very complex proposition to keep track of what's out there. If you guys have looked at GitHub, I kind of like it, but there's kind of a downside to it too. It's open source, so you kind of don't really know what you're getting. When you're working with Linux, they do updates to Linux a lot. So, even when you're using open source software, you have to be very careful of which version of the software you're pulling, and make sure that if you're embedding that into a hardware device, you got to make sure that you know what your hardware is and know what the open source software is that you're running with. Number of software standards. Talked about 2167, that's for military work. DO 178 is for the Federal Aviation Administration. As you can imagine, like if you're putting software into an onboard computer for a 767, you really want to test it, and you really want a lot of people looking at that software to make sure that there are no errors in it. In fact, I had a job at Boeing one time where that was my job. I had to go over the unit tests that were performed by Honeywell, and we had to capture and document those unit tests, make sure that those were stored and available for the FAA. When I was working at General Electric on the thrust management computer for the 767, at one point they didn't follow these standards. So I came into work one day and they had yellow tape up on all of the equipment, and we were not allowed to touch the equipment until the problem that was found was resolved. So it's a serious thing. When you're working for a government entity, they have the power to come in and shut down your project. And when you've got like 30 or 40 software engineers that's working on this project for $70, $80 an hour, and they're just sitting there idle, that can be a real problem. Not to mention if you introduce a software bug. In software configuration management, I have a consultant come in that's doing that work, and he tells the story of a company that was put out of business because they had an error in the software configuration that got like a testing program got confused with the operational software, and they placed an order for $30 million worth of stock by mistake. So by the time they got the error sorted out, it's like the company went bankrupt. If your software fails, in a flight computer, it could cause an airplane to crash or loss of life. So it's very important, when you're doing professional software engineering, these standards and adhering to them are very important. If you ever find yourself in the situation where you need standards to start with, the IEEE has a number of them out there that are well recognized by industry that will give you a starting point, so you can start with those and then add to them or cut them down if you need just like a template or something to give you some ideas about creating software standards. Prior to these, many companies were developing their own. I know Boeing had a set of software standards, but since they were doing so many military projects, when 2167 came out, they just basically adopted those. So if you're ever in management, or if you're ever in like a software configuration management position, always try to find the company standards. A lot of times, like the programmers don't want to follow the standards, but if you can at least point to the company standards, then at least you have something to back you up. We will be using UML in here. UML stands for Unified Modeling Language. It's the de facto modeling language for software development. It's a unified language because it took the work of Ivar Jakobsen, James Rumbaugh, and Grady Booch. They were all working on modeling languages. Jakobsen, you still see articles from him. He writes in Communications of the ACM, and so he still publishes articles. He wrote this book, Object-Oriented Software Engineering, and he's the one that came up with use cases. We're not going to be using use cases in here, but it's a object-oriented software engineering, a use case-driven approach. So again, this is a fundamental book in software engineering. Rumbaugh was working for General Electric. He and Booch were working with how to depict classes. So I think Rumbaugh depicted class diagrams as squares, whereas Booch had little cloud symbols. And Booch was really active in the 80s. He worked for Rational, who created Rational Rows. But they also had workstations that implemented Ada. And so he's really the industry, he's worked a lot in industry at a lot of different companies. If you take CSCI5555Fall2017L1P1, this is the book we use in there, Object-Oriented Software Engineering using UML and patterns. So in 6620, we do a lot with use cases, scenarios, sequence diagrams. We create the functional model, the dynamic model, and usually, what I do for the project is I'll take one of the projects that we're currently working on, and we will create a requirements analysis document with the use cases and sequence and collaboration diagrams and state charts embedded in it to present the requirements. It's like a requirements analysis document. You know, you have the list of requirements, but it's also very valuable to do some upfront modeling. Just quickly, a use case tells what the software product is going to do from the viewpoint of the user. When I was at Harris, one thing I did is like I added some functionality to this software-defined radio, and I kind of did it in reverse order. You know, it's like I did the implementation, but then I backed out some use cases so that the customer could look at the use cases and understand what functionality was added to the radio. So there, you know, there's no book that's going to tell you to do that. So if you want to continue in software engineering, the key is to learn the tools, and then for whatever project you're on, be comfortable enough to use those tools to accomplish the task at hand, whatever that may be. We will be using Visual Studio. If you have Visio installed on your computer, there is some limited capability to take a class that you've implemented in Visio Studio and reverse engineer the UML diagram for that class. And so that can be useful too. Again, you know, learn the tools, learn what's out there. I'll guide you through some of them, you know, just so you get an idea of what the tools do and how they use. But again, there is no cookbook way for developing software. You know, it's like every project is different. The tools and the techniques that they use are different. So if you're going to go into software engineering, definitely learn how to code. That's fundamental and that's key. But you know, you're going to be competing with people that go to coding boot camp, where they spend time just learning code. So what you should do here at the university is try to expand your knowledge to use these tools that we'll be covering in here, and it'll just help you when you go to look for your first job. Also, if you want to be a software engineer, try to get on a project like later in your studies, because I'm telling you that's always what employers ask. They're kind of unimpressed with the list of classes that you have, but if you can point to some projects that you've been on, you know, it's like, for instance, on the VMC project, the project engineer working on that is now working in industry as a project engineer. And in fact, I can say the same thing for the project engineer on the predictive wastewater management system. Get on a project, and that's your fastest way to get in to a position. Okay, let's see, how are we doing with time? Why don't we take a break, 10 minutes, and then we'll pick it up at like 7.
Can I look in the back, because I love something?
Oh, yeah, sure. Yeah, go ahead.